Hello all, welcome to the Basics.Academy. This is Smart Contract Security, Fundamentals and Auditing, a 5 units, 3 credit course in the BSc Blockchain Technology program. Let's get into it. Today let's have a look at the different variants of reentrancy in action. First, we are going to check the single function reentrancy. Here we have the vulnerable vault smart contract. Now inside the smart contract, from within the withdraw function, there is a reentrancy bug. How do we know there is a reentrancy bug? Because the balance of message.sender is being updated after the external call. Coming to the right side, we have created a reentrancy attacker contract. From within the constructor, we pass in the vault address, which is going to be the deployed address of vulnerable vault, and we are setting that vault address into a variable vault, which is of type iVault. Now, what is iVault? iVault is an interface which has two functions, deposit and withdraw. Coming back to the reentrancy attacker, here we have our attack function. From within the attack function, we check that the passed amount of ether is greater than 0. If yes, we set that message.value into a local variable called as seed. After that, we invoke vault.deposit. When we invoke vault.deposit, it calls the vulnerable vault's deposit function. On calling the vulnerable vault's deposit function, whatever the amount that we have sent, that is being assigned to the state variable balance of. This is necessary because in withdraw function at line number 31, we check that the amount must be greater than 0. And this amount is fetched from the local or vulnerable vault's state variable called as balance of. Once we have made a deposit, then we call vault.withdraw. Coming back to the vault.withdraw, the vulnerable vault loads the balance of message.sender and stores it into a local variable called as amount. Then it checks that the amount must be greater than 0. If the amount turns out to be less than 0, in that case, it will fail, showing nothing to withdraw. And then it makes an external call. As soon as it makes an external call, the reentrancy or the control leaves here and the control goes to the vulnerable or reentrancy attacker smart contract. Once message.sender.call is executed, in this case, message.sender is nothing but a reentrancy attacker smart contract. Since you are passing ether, so what happens? The call directly goes into reentrancy attacker's receive function. Now here's the catch. Inside receive function, we are checking address of vault.balance. If it is greater than equal to seed, what is seed? The initial amount which we have stored into the seed state variable, as long as the vulnerable vault's balance is greater than seed, it will go on calling vault.withdraw. And when it calls vault.withdraw, the balance of message.sender always returns non-zero because this balance of message.sender was updated after the external call. So what happens? Initially, the attacker invokes attack, deposits, say 1 ether into the vulnerable vault, then calls vault.withdraw. So this check passes and the external call happens. When the external call happens, the call comes back to the attacker's receive function. From within the receive function, it checks if the balance of the vault is greater than seed, then again call withdraw. Again external call, again receive, again call withdraw. Again external call, again receive, again call withdraw. So this goes on as long as the vulnerable vault is not drained out completely. So this is single function reentrancy. This is the attack. Now, how do we fix this? There are two options. First, make use of ReentrancyGuard. So what is ReentrancyGuard? This is a minimal implementation of OpenZeppelin's ReentrancyGuard smart contract. What it does, it has a modifier nonReentrant. Whenever you add this nonReentrant modifier on any function, when the function gets executed, during execution, the status is set to entered. And what happens if the code again tries to re-enter that function? It will check and the status should not be entered. If the status is entered, it will return an error, ReentrancyGuard, reentrant call. So this is our first defense mechanism, which is ReentrancyGuard. Let us now look at our SafeVault smart contract. Here you can see in SafeVault, right? It implements iVault and ReentrancyGuard. The deposit function is the same as that of VulnerableVault. However, in withdraw function, there are two fixes applied. First is the CEI pattern or check effects interaction pattern. And then secondly, we have applied the non-reentrant modifier. What exactly happens? Whenever the withdraw function is called, it implements the non-reentrant modifier. So what it does, whenever the non-reentrant modifier is invoked, so first it will check the status should not be equal to entered. Initially, the status is not entered, right? So it checks the status should not be equal to entered. If that is true, it will set the status to entered, and then this underscore will be replaced by the withdraw function body. This underscore will be replaced by the withdraw function body. So what do we know as of now? That status has been set to entered and withdraw function is getting called. Let us take the same example of our reentrancy attacker contract. Here, the vault address is that of SafeVault. The attacker calls attack function. It calls vault.deposit. When it calls vault.deposit, so the balance of reentrancy attacker is set to a non-zero value. Then it calls vault.withdraw. On calling vault.withdraw, first this modifier is invoked, which sets status equal to entered, and then the withdraw function starts executing. Look, here we have already updated the balance to 0 before making the external call because we have applied both the fixes, check effects interactions pattern and the non-reentrant pattern. After applying CEI, then we make an external call. When we are making an external call, similar to the first one, the call comes into receive. It will check that the balance is greater than seed. If yes, it will call withdraw. However, when it calls withdraw for the second time, again this non-reentrant modifier kicks in, and this non-reentrant modifier checks that the status should not be entered. But remember, the status is set to entered, and this is where the withdraw function is getting executed. So this required condition fails, and hence it shows or the transaction reverts with the error ReentrancyGuard reentrant call. That is, the attacker is now not able to again call withdraw function via a loop. So this is how you mitigate single function reentrancy. You make use of two defense mechanisms. First is the reentrancy guard and second is the check effects interactions pattern. How can we test that? So here I have written reentrancy test.js file. This is funded DAO function which takes in the contract name. First it will take in VulnerableVault smart contract name, and secondly it will take in SafeVault contract and create the vault contract object. After that, it will deposit say 5 ether from two accounts into the DAO contract, and then it will return the DAO and the attacker account. So in the first test, what we are doing is attacker drains the entire pool. Just look at the test cases. It is nothing but it sounds like or feels like plain English statements. First, we get the DAO and attacker account by calling the funded DAO function. Then we check that the balance of the DAO address is equal to 10 ether. Why? Because we have deposited 5 ethers each into the DAO contract. After that, we deploy the attacker contract. Once the attacker contract is deployed, we connect the attacker account to the attacker smart contract and call the attack function. When we call the attack function, what happens? The reentrancy attack happens. Now this says after the attack has been executed, so we are just console.login. How much ETH does the DAO contract has? This will show the DAO contract has 0 ETH because there was a reentrancy bug. However, when we use a SafeVault, in that case, the reentrancy bug will not happen. After having a look at all the test cases, let us now run the test cases. The test cases for reentrancy can be run using the command npm run test reentrancy. Let us do that. Here I am on terminal, npm run test reentrancy. Just look at first, when the vault was vulnerable, that time the attacker was able to drain the entire pool. When we say pool, here pool is nothing but our vulnerable vault smart contract. So after the first test case, the balance of the pool is 0.0 ETH and the attacker took away 11 ETH. Since we deposited 5 ETH from two different accounts and the attacker has deposited 1 ETH initially. Hence, after exploiting the reentrancy attack, the attacker got 11 ETH. Now the second test case, the identical attack fails and the pool is untouched. Why? Because we are using the SafeVault, which makes use of check effects interactions pattern and the reentrancy guard. Let us now deploy the contracts using Remix and try out does exactly the reentrancy works as expected and whatever we have seen through the test cases and also by the contracts, does that hold? So what I have done, I have created a smart contract called a single function.solve and I have copied the entire code from VS Code. And here I want remix INE of inside remix INE. So let us do step 1. First, deploy VulnerableVault, then deploy reentrancy attacker, then call attacker.attack. Select VulnerableVault. VulnerableVault is selected. Click on deploy. This VulnerableVault is deployed successfully. This is the VulnerableVault contract address. Copy it. Second step, deploy reentrancy attacker. And in the constructor, we pass in the wallet the VulnerableVault contract address, which is BD ending with C5. That is correct. Now click on deploy. Now go to VulnerableVault, click on deposit. So from account 2, we will deposit 10 ETH. From account 2, we will deposit 10 ETH. So here it is Ether, can't transact, and the contract's balance is 10 ETH. Here, let me change or go to account 3 or I'll select account 4. From account 4, I will initiate the attack. So here we have the reentrancy attacker. Okay, message. Reentrancy attacker. Attack function. Pass in 1 Ether, and click on transact. As you can see, 10 ETH has been moved out from the VulnerableVault contract to the reentrancy attacker contract. Let us now move this 11 ETH to the hacker account. Open this, reach the address, click on transact, sweep address, what does it show? The transaction, okay. Since it is a non-payable function, so we should not pass any value to it. Click on transact. Now the transaction has gone through and the balance is reduced to 0 of the reentrancy attacker contract. Here if you check, account 4 started with say 100 ETH and now it has 109.999 ETH. So what we have done is we have performed step 1, 2, 3, 4 successfully. Now we are going to repeat the same steps, but instead of VulnerableVault, we are going to deploy SafeVault. Let us do that. Let me delete this contract instances because anyway we are going to name new ones. Also the transactions done. So from here, select SafeVault, click on deploy. SafeVault is deployed. Copy SafeVault's address. Now select reentrancy attacker. Vault address will be the address of SafeVault. Click on deploy. Reentrancy attacker. Okay, so we remove this and try again. deployment of reentrancy attacker. Okay. I was passing in the transaction hash. Hence, the deployment failed for the first time for reentrancy attacker. I should pass in the safe vault address. This is the correct safe vault address. Now click on deploy. Done. So here we have a safe vault and reentrancy attacker deploy. Let us go deposit from account 4 itself, and we will deposit say 10. I need to did not transact. Deposit successful because safe vault's balance is now 10 ETH. After that, go to reentrancy attacker, click on attack, change the account to say account 5. Account 5 has 100 ethers in it. It will call attack function with 1 ether. However, this is going to fail. I can't transact. This got failed. Reason provided by the contract, each send failed. In case of SafeVault, the reentrancy did not happen because we have added 2 fixes. First is the CTI pattern and second is the non-reentrant pattern. Hence, the transaction got reverted and the reason provided by the contract was each send failed. Prior to closing up, let us withdraw the 10 ETH from SafeVault. Select the function withdraw 10 Ether, and this should be called from account 4 because account 4 had earlier deposited 10 ETH input. And here we are, SafeVault withdraw with 10 from there. Already show it. Okay, the call function should be payable. Should be 0. And the withdraw function, here it is. Function withdraw does not take any argument. Then we call transact. After calling transact, notice the 10 ETH is now being 0 and account 4's balance is again set to 109.999 ETH. So to wrap up, we have covered single function reentrancy, wherein first we checked with the vulnerable vault, we were able to compromise the reentrancy bug and drain all the funds, and then we applied the fixes of CVI and reentrancy and verified that reentrancy does not exist anymore. That wraps up this session. If it helped, like and subscribe so you don't miss the next one. Questions? Drop them in the comments below. See you in the next lecture.